Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on partial differential equations. Now the focus of this presentation is on applications of the method of Laplace transforms. And we're going to solve the following problem using Laplace transforms. Now this is going to be a reasonably long presentation, and there's 3 steps to the example that I'm going to do. First of all, we're going to solve this problem using Laplace transforms. Then we're going to demonstrate that the answer that we've produced is a genuine solution, so we're checking our results. And part C is an interesting question. We're asked, will the method of separation of variables work for the problem that we solve using Laplace transforms? Now, if you're familiar with partial differential equations, or you may have studied it in a previous course, you may be familiar with the method of separation of variables. Now, part C is a really interesting question because it's asking you, can the method of Laplace transforms do something that the method of separation of variables cannot do? Okay, so we're going to work our way through each of these steps and just work through it. Okay, so just to refresh your memory, for functions of 2 variables, we define the Laplace transform of, say, a function of x and t by this integral. The Laplace transform is an integral transform. Okay, so here we've got big T here. I'm going to represent the Laplace transform of big T by big T bar. Okay, now when we solve differential equations, transform of derivatives are very important, and I've discussed these in previous videos. Now, just to refresh your memory on the algorithm, if you like, for solving these kinds of problems, you start with a PDE, you transform the problem to form an ODE, you solve the ODE to get the transform of the solution to the original problem, and then you use the inverse Laplace transform, to transform everything back, so you recover the solution to the original problem. Okay, so they're the steps for solving part A. So let's get down to it. Okay, so let's transform both sides of the given differential equation. And in all cases, we're transforming with respect to little t. So TOD, transform of derivatives, gives the following. Well, we're going to use this, and we're going to use this. Okay, so let's do that. So T bar is going to be the transform of big T in this context. Oops, sorry. That's just a regular big T there. Okay, no bar. Okay, so we've used transform of derivatives. We can clean this up a bit by using the fact that this is here, so that's 0, and so we come up with the following ODE. Now, why do I call this an ODE? There's partial derivatives present. Well, the point is that there's only one partial derivative present, a second order one, and in this case we can think of this as an ODE, really, because we can use ODE, or ordinary differential equations, methods to solve it. Okay, so you know how to solve these kinds of problems from a first course in differential equations. So let's investigate this further. So imagine S is essentially a constant now. How do you solve it? Well, it's a second order linear homogeneous ODE with essentially constant coefficients. So we look at the so-called characteristic equation. It'll be lambda squared from that minus S equals 0. And so solving for lambda, and S is positive here, we get the following. Now these are going to be real numbers, and you can see that they're not equal. So from this observation, the solution to this problem has a special form. T bar is going to be the following. Well, it's a linear combination essentially of exponentials. Okay, so now usually when we're solving ODEs, these coefficients will be constants, but remember T bar is a function of two variables here. So really what we should have is, let's see if I can squeeze this in, A and B depending on S. Okay, so this is the general solution to this problem. Let's refine it now by calculating A of S and B of S. Okay, so we've moved from here to here. We're in the process of moving from here to here at the moment. Okay, we're trying to solve the transform problem. Okay, so determine A and B from our extra conditions. Now we've used this already in here. We haven't used these yet. Okay. So how do we come up with this? All right. Well, well, firstly, what we'd like to do is get the conditions 3 and 4 in terms of T bar. Okay, so how do we do that? Well, let's consider condition 4. Okay. Well, actually, no, let's consider condition 3. Okay, so we have a limit, and let's just consider it with respect to T bar, as x goes to infinity, of T bar xt. What is this? Well, this can be written out just from the definition of the Laplace transform. It's the following. And sliding the limit sign inside the integral sign, then we get the following. Okay, well, if we look up here, we'll see that the limit of this must be 0. So this integrand must be 0. Okay? Well, what does this mean? It means that if we go up to my general solution, that I can now calculate one of A or B, essentially because I've produced a new condition involving T bar rather than just T. Okay, so let's call this the general solution star. Let's take the limit of this as x goes to positive infinity. Okay, remember s is positive in this context, so this will certainly go to 0 as x goes to infinity. But what about this? Well, this can only go to 0 if the coefficient is 0. So we've calculated big A, it's just the 0 function. So this term really disappears. Okay? What about this term? We want to find the coefficient b of s here. Okay, so I'm going to take this condition out, condition 4, and see if I can recast that into something useful. So what I would like to do is have it in terms of something like this. Now what is this? Well, it's just the following. Okay, and if I go up here, well, this is just 1. So it's the Laplace transform of 1. Now the Laplace transform of 1 is just 1 on s, which you can calculate directly or from a table, for example. So what does that mean? Well, I now have another condition that I can team up with star to get b of s. So this was all from 4. Okay? Okay, so let's go up here, sub in x equals 0. I know this term is 0, so the exponential will just go to 1. And I know that this has to equal 1 on s. So I've just computed big B now. Big B of s is 1 on s. So I've got my A and my B. I can now refine T bar, and basically I've solved the transform problem. Okay, so we're now at the stage where we're trying to invert from here back to here to recover the original solution. We've solved the original problem. Now to invert back, I'm going to use the following identity. The Laplace transform of 1 minus the error function of this is equal to this. This means that if I want to invert this, I'll just get what's in the curly brackets here, 1 minus the error function of this. So that's what I'm going to do with this problem. You can see that this and this are essentially the same. You would just replace A with X. Okay? So the solution to our original problem is the inverse transform of T bar, which is just the inverse transform of this, which, from this identity here, and I'll prove this in another video, this is not an easy transform to come up with, is just the following with A replaced by X. Okay, where this ERF is the so-called error function, which is a special function in applied mathematics. Okay, so you can also write this in the following way, just as a complementary error function. Okay, so if I wanted to write this out in full, I could write it out in the following way. It's 1 minus 2 on root pi x on 2 root pi 0 e to the negative, say, u squared du. Okay, so we've solved the problem now. We're at the final stage. We've recovered the solution to the original problem. Okay, so let's move along and try to answer part B. Demonstrate that your answer up here is a genuine solution to the original problem by illustrating that your answer satisfies each of the above equations. So we've come up with this solution. Let's actually check that it really is correct. Okay, so there's a little bit of differentiation involved and checking of the associated conditions. Okay, so let's just work our way through it. So for part B, let's take what we have here and compute the derivatives in our PDE1, and then we will hopefully show that it holds. So from this expression, let's compute the following. All right, so let's use the fundamental theorem of calculus. We're differentiating the integral here. So if we differentiate with respect to t, what we're going to do is get the following. The derivative of this with respect to t is going to come to the front. And then what you're going to do is get rid of the integral sign and replace u with x on 2 root t. So we're going to get something like the following. Okay, we're going to get this times the derivative of what's up there with respect to t. So that's going to be something like this. Times the integrand evaluated up here at the upper limit of integration. So that's going to be something like the following. Okay, so that's t sub, big T sub t. Now if we differentiate this with respect to x twice, again you apply the fundamental theorem of calculus 2 times. Okay, so if you do that, well, on the first differentiation you will bring 1 on 2 root t to the front, the integral will disappear and you'll be replace u with this again, and then you would differentiate it again. Okay, now if you do that, you'll get the following. Okay, so if you compare this with this, you can see that they're going to cancel out. So, 1 definitely holds. It's just a matter now of checking the other conditions. Okay? Alright, so what are the other conditions? Well, we've got this condition here. So if we go up here and replace t with 0, you'll go, okay, well, obviously we'd be dividing by 0 there. Now we would interpret this then as an improper integral from 0 off to positive infinity. Okay, and we want that to be equal to 0. Okay, so it would be 1 minus this going to infinity. Now, this is just essentially an integral that we can calculate. Okay? This special integral here is just root pi on 2. So, and I've shown that in other videos. So this will become 1, so this is 0. So 2 holds. Okay, what else have we got? Well, we've got these limiting conditions. So let's have a look at that. As x goes to infinity, this upper limit will go to positive infinity, so it'll be basically the same as this condition. We want it to be 0, so, and it will be because this will just be 1 minus 1. So now let's check this limiting condition. So we need to differentiate this with respect to x and then take the limit. So if I differentiate this with respect to x, I should get the following. So again, fundamental theorem of calculus. 1 on 2 root t is going to come to the front. And you replace u with x on 2 root t. So what happens as x goes to infinity here? Well, this exponential is going to drag everything down, so this will actually go to 0. Okay, so hence 3 hold. Okay, now I'm sort of using 3 as 2 equations or 2 conditions there. The last thing we've got to do is show that this satisfies 4. So as x goes to infinity, when x equals 0, what's going to happen? Well, this upper limit of integration will be 0. So I'm integrating from 0 to 0, that will be 0, and I'm left with 1. Okay, this will be 0, so 4 holds. Okay, so we've now finished part B. We've shown that this is a bona fide solution to our original problem. Okay, so the last part of this presentation is, will the method of separation of variables work for this problem? Okay, this is an interesting question. Okay, because what it suggests is that the method of Laplace transforms can do something that the method of separation of variables can't do. So let's explore this further. Okay, so for part C, as you do with any separation of variables problem, you would consider a solution of the form like this. Now I've used big Y instead of big T because big T is already here, okay? So you've got the independent variables sort of, I guess, separated in some sense through this multiplication. Okay, what you would do is you would compute this derivative and write them in terms of the derivatives involving big X and big Y. Okay, so differentiate this with respect to little t, you'll get the following. And if you differentiate with respect to x twice, then you'll get little x, then you'll get the following. So the dashes here just mean differentiation with respect to the independent variable of the function, whatever it is. Okay. So then let's write these out in terms of this partial derivative, a partial differential equation, and let's see what happens. Okay, so it's, I can replace this with this. Now I'm going to drop off the arguments of big X and big Y just to save a bit of space. And this is over here. Okay, now if I separate the variables, then Okay, so I'll get the following. Because this left-hand side is a function of little x only, and this right-hand side is a function of little t only, these ratios must be equal to a joint constant called a separation constant. Okay, so imagine varying the left-hand side by varying little x. We'd expect the left-hand side to vary, but the right-hand side can't vary because there's no x's over here. Similarly, imagine varying this right-hand side by varying little t. This side is expected to vary, but this side can't vary because there's no little t's over here. Okay, so let's write our separation. The only way of explaining that is that there's a separation constant, lambda, which is the joint value of these ratios. Okay, so now what I can do is build two ODEs out of this involving lambda. We're going to have y prime equals lambda y. And we're going to have x double prime minus lambda x equals 0. Okay? Okay. So what we'd like to do is solve these, and I can solve this first order ODE immediately. It's going to be something like an exponential function, where a is a constant. Okay. Now let's look back at our conditions again. If this is a solution to this problem, big Y, we've kind of, it looks like we've found half of our solution up here. Okay. If we look at 2, condition 2, what is condition 2? Well, in the format of this product, condition 2 is the following. Okay, it's the product of this times big T of 0. Now, what this means is that big T of 0, big Y of 0, let me adjust that. Okay, big Y of 0 must be 0. If this is 0, then essentially this thing must be 0. So we only have the trivial solution. Okay, so big Y of 0 equals 0. What does this mean? Well, if you compute your A from this, so put in T equals 0, you'll get 1 here, 1 times A. And over here you'll get 0. So what this means is that big A is 0. So what does that mean? It means that this must be essentially the trivial solution. So that must be the trivial solution. Okay, just the 0 solution. Okay, what does this mean? Well, we've got the 0 solution, which isn't very interesting, but more worrying is now this condition. Because what this says is that big T has to be 0 for all x and all t, including x equals 0. But what condition 4 says is that at x equals 0 and all little t, the big T is 1. So this and 4 are incompatible. Okay, so what do we conclude then? We conclude that the method of separation of variables will not work for this problem. Okay? Okay, so that's pretty interesting. We've now discovered something that Laplace transforms can do that the method of separation of variables can't do. Now, before I sign off, I just wanted to give you a little bit of insight into what this problem might represent. So we've got a heat or diffusion equation. Big T might represent the temperature at position x and time t of some semi-infinitely long bar. And you can see that initially, at time t equals 0, the temperature is 0. You've got these limiting conditions on the temperature and this flux type condition. And at the end of the bar, corresponding to x equals 0, the temperature is just a constant for all t. Okay, so that's some modelling context to relate this equation back to some sort of modelling process. Now, in other presentations, I will continue looking at Laplace transforms and their applications to PDEs. I hope you can join me for those presentations.